Hello, everyone, and welcome to our last lecture in thermodynamics. So next time we're going to be moving on to phases. But before we do that, I want to go ahead and finish up dealing with the influence of the free energy of a gas phase species. So last time we generated an equation of how the free energy of a gas phase species has a pressure dependency with respect to, say, a reference temperature, typically our good old friend 1 bar. Now, one of the real problems of this approach is that it assumes that all gases behave ideally. Otherwise, it's a great simple equation, and we'd love to be able to use it to treat all of our various systems because it meant so many of our descriptions of gas phase behavior is built on this pressure dependence of gas with pressure. So, one of our classic tricks of how we can essentially treat a system is say, well, I'm going to keep this equation intact, but I'm going to change this key variable. So now, if I've got a system that behaves unideally, I'm going to replace, non ideally, I'm going to replace pressure with fugacity. And F is essentially going to be our fugacity, which is a way to describe the effective pressure if the gas was ideal. So let's say I have a gas with a measured pressure of 1 bar, but chemically it acts like a gas, an ideal gas with a pressure of 0.99 bars. So in this case, the fugacity would be 0.99. And this would be gas that we would traditionally consider relatively ideal, but it's not quite. And so this is essentially one of the big issues with fugacity is that, well, that non-ideality ends up influencing the effective free energy of a species, which then affects what chemical reactions are likely to happen. So we can essentially try and relate the difference in between our fugacity and the actual measured pressure of the system by what's called the theta, or the fugacity coefficient. So our fugacity coefficient is really just a ratio of our effective pressure, so what the gas acts like, and what the gas really is. So if a gas, say, has a lot of attractive IMFs, well, it's going to be spending less of its time exerting pressure and interacting with the external system. And so it would have a fugacity coefficient that would tend to be less than 1, as it's going to act like it has a pressure less than it actually does. If, say, I have a non-ideal gas like highly compressed neon, where everybody is essentially bumping into everybody else and it's trying to get away and react with anything possible, well, it's going to have an effective pressure much higher than the measured value. So at this point, we'd have a fugacity coefficient much greater than 1. And this is really what the fugacity coefficient is giving us a difference in a general idea of the relative non-ideality of the system. And in practice, we can essentially try and measure the difference of the system in its ideal versus non-ideal behavior based on its chemical interactions. So it's not too surprising that our fugacity coefficient will be related to essentially the free energy of our actual species and the free energy of the species of uh, the free energy of the species if it was ideal. So the free energy of the species under these non-ideal scenarios would essentially be the free energy of the species at 0 bar plus the integral of 0 bar to the actual measured fugacity of the system with this simple equation. Because again, all of the non-ideality went into this variable. And dp is just simply going to relate the progress from our native conditions to this new pressure. However, the actual pressure of the system is, well, something else. So I can start from the same base point, and now I'm going to be integrating to the actual pressure of the system. So when I'm taking the difference of these two values, well, you're going to notice that our two reference points essentially disappear, and then all I have is the difference of these two integrals. Now, since the whole premise of this idea is that I'm able to treat the system as if it was ideal, well, I can essentially treat both of these molar volumes with the ideal gas law. And so I'm going to have the integration from 0 to f of RT over the pressure, and the integral of 0 to P for the same equation. Well, both equations are going to essentially generate RT because these are constants and will come out forward. And then our good old friend, natural log of our good old integral dP over P, which gives us a natural log. Now this one would give us the natural log of F, which we have, minus the natural log of 0, which, well, that ends up disappearing because, well, ends up giving us a natural log of 1, but that ends up disappearing because so does this guy. So the two reference pressures end up canceling out. And so all we end up with is the difference between the RT of the natural log of F and the RT of the natural log of P. Now, because we are great fans of log laws, the difference of two logs is essentially the same as the log of the ratios. So at this point, what we find is the free energy difference of the actual versus ideal pressures is going to be the same thing as RT of the natural log of our fugacity. So if you know what the free energy of the species is supposed to be based on the measured pressure, and you have some way to measure the free energy of the actual compound, well then congratulations, you found a way to directly measure the fugacity of the system. However, one of the other very useful things we can do is we can also determine the fugacity in terms of the compressibility. So this is our good old friend Z from our real gas laws. So by definition, we know that the natural log of our fugacity coefficient is the natural log of the ratio of fugacity to the pressure. And we can essentially back up what we did on the previous slide and treat this as the integral of 0 to f of RT over RT over V dP minus 0 to P of, again, the same expression. So again, this will be equivalent to what we did on the previous slide because we have no RT. So using this relationship, we can then go ahead and express our fugacity term as now an integral of 0 to, instead of 0 to f, from 0 to P, but now I've incorporated all of that non-ideality in terms of the compressibility coefficient. If you like, one way to verify this is we can go ahead and replace this with the molar volume over the ideal Z times the molar volume of RT over RT, and then again, the same thing here, and then substitute it back, and we get this Z expression essentially remaining when we go from F to P. So again, by going from non-ideal to ideal, this Z expression pops out in our integral. Now, these two integrals are exactly the same except for this Z expression. So we can generate the natural log of our fugacity coefficient in terms of the integral from 0 to P of our compressibility factor over P minus 1 over our pressure dP. So, okay, this is a little bit of a cumbersome sort of integral, but our two pressures will essentially go ahead and condense. And not exactly the best integral we've encountered. But what this allows us to do is if we have an analytical expression for our compressibility factor, well, then I can substitute that in, run the equation and the integral, and we're going to be able to determine the fugacity of the system. However, one of the things I really want to illustrate is that it turns out that the fugacity coefficient of the system is going to have a pressure dependence because, again, The value is going to depend on how far into this equation I integrate. And again, as we've seen previously, my compressibility factor will also see a temperature dependence. Now, again, this isn't exactly the most useful sets of equations we've worked with, but there's an important thing to remember. If my system, say, relatively obeys van der Waals gas, which is a fairly reliable system, well, it turns out all van der Waals gases have the exact same equation in reduced coordinates. So it turns out we can actually generate fairly universal descriptions of our fugacity coefficients with respect to our compressed variables. So what we have here is a plot of fugacity versus reduced pressure over fairly large pressure regimes. And again, under fairly large pressure regimes, our Z values almost always tend to be greater than 1, so we almost always see a positive deviation from ideality, and we see the same thing with our fugacity coefficients. The system will always act with a higher free energy value than would be predicted from ideal behavior. However, if you're, and this expression is essentially uh, emphasized as we start reaching critical temperatures that are much lower. So again, a cold system at high pressure is going to act with a much higher fugacity coefficient and thus a much higher free energy than we would normally expect from ideal systems. In fact, as much as 2 or 3 times as high. However, when we're working with, say, lower pressures, then we can start seeing this negative deviation from ideality, which also demonstrates it with a fugacity coefficient of less than 1, which means that my fugacity of the system is less than the pressure, which again generally indicates um, a free energy of the system, which is essentially lower than would be expected from ideal scenarios. So as we're going to be going forward, we're going to be making a lot of use of the free energy of gases. And in these equations, I'm almost always going to be making use of the pressure of the system. And I want you to be very aware that you can replace the use of pressure with the replacement of fugacity and be able to describe systems that are a lot less well behaved. And again, if we're working in reduced coordinates, it can actually be a fairly easy substitution, but one that you have to be aware of that may be present. So next time, we're going to be dealing with one of the simplest sets of chemical changes. It's time to get into phases. Till then, take care.